I'm so glad you're here for another episode of Mechanism Monday, where every Monday we write out the electron-pushing arrow mechanisms for different chemical transformations. In last week's video, I asked if you could solve the mechanism for this chemical transformation, so if you haven't had a chance, pause the video now and try it independently. And make sure you stick around to the end because I'll give you another mechanism to solve for next week's video. So this is a really unique reaction in which we're starting with this acyl azide, and it undergoes a series of rearrangements to end up with a 7-membered ring that contains an amide bond in it. And interestingly, this reaction was actually published way back in 1965. The first step of this reaction is actually going to be the loss of nitrogen gas. So importantly, this structure also looks just like this, where we have our carbonyl group here, and the azide portion, remember, actually looks like this, where one of the nitrogens are negatively charged and the other is positively charged. And that first step is actually what's known as a Schmidt rearrangement. So a Schmidt rearrangement is going to take this acyl azide, and these electrons here are actually going to shift to being attached to the nitrogen. So this carbon will now be attached to this nitrogen. And in doing so, these electrons are going to leave, which allows us to liberate nitrogen gas. So nitrogen gas will evolve from this reaction. So then the product of this reaction is going to contain now that carbon to nitrogen bond, which is going to contain a double bond to carbon, which is still has a double bond to oxygen. And from here what happens is actually a 3x3 sigmatropic rearrangement. So a 3-3 sigmatropic rearrangement, which you probably learned about back in organic chemistry. So these pi electrons will move to being between these two carbons, which will liberate this carbon-carbon bond to be located between this carbon and this nitrogen. And this pi bond is actually what serves to close that ring. So this is a 3x3 sigmatropic rearrangement. And this is actually how we generate this 7-membered ring. So the 7-membered ring is now formed where we have our nitrogen here and our carbonyl functional group, and importantly there's a double bond here and a double bond here, because remember these electrons have traversed over to being located in different positions, and the carbon to nitrogen double bond was formed here. What happens next is a protonation from H3O+, so acid is present in this system, and what happens is this protonates the nitrogen atom located at this position. So we will protonate at that position to generate water. And this is how we form this new nitrogen to hydrogen bond. So now we have our 7-membered ring. And importantly now, this nitrogen has a hydrogen on it. We still have the carbon to nitrogen double bond, and then we still have our carbonyl functional group. And then we still have this carbon to carbon pi bond. Now importantly, what happens next is going to be deprotonation of this carbon-hydrogen bond. Because this is now positively charged at nitrogen, you can think of this as like an alpha carbon hydrogen, just like in carbonyl functional groups, which can be deprotonated to make enolates. In this case, this iminium ion, which has been formed, makes this hydrogen proton very acidic, which can be deprotonated by water. So the water that we formed in this step here can actually come and deprotonate this hydrogen, which is going to move these electrons down to make our new carbon to carbon double bond. And then these pi electrons will come over here to be on nitrogen, giving us our neutral amide bond, which is how we form this final product. So interestingly, several of these reactions, like a 3x3 sigmatropic rearrangement and alpha carbon enolate chemistry, are chemistry that you probably learned about in organic chemistry. So even though this transformation looks relatively advanced, if you take the pieces of information that you learned about in your courses, you can also solve these complicated mechanisms. If you enjoyed this week's mechanism, make sure to give it a thumbs up down below. For next week's video, I'd love to see if you could figure out the mechanism for this chemical transformation. Drop it as a comment down below if you have any ideas, and make sure that you subscribe to the channel so that you never miss another Mechanism Monday. I'll see you next week.